All right, guys, let's talk about the second derivative test. And first thing I want to do is just talk about, well, let's take a look at a situation where I have a maximum. If this point is a maximum of some sort, then it's pretty obvious that this graph has to be concave down. And of course, we know that concave down means that the second derivative is less than 0. The slope of this curve is going from steep to less steep. So the second derivative is 0 because the derivative is decreasing. Similarly, if we're looking at a minimum, this clearly is concave up all the way around. The slope is going from a negative to a positive. The second derivative is positive because the slope is increasing. And the second derivative test then basically says if f prime at some number is 0 and the second derivative is less than 0, then we have a local maximum. If f prime is 0 and the second derivative is greater than 0, then we have a local minimum. So notice that this test fails if the second derivative is equal to 0 or does not exist. And so we'll still have to do some of that first derivative stuff that we did earlier doing the analysis in situations where, in fact, this just doesn't work. But if it does work, it's a pretty cool little shortcut. So let's do a quick example. This is example 6. Given a function f of x equals x cubed minus 12x minus 5. The first derivative is 3x squared minus 12. We want to set the first derivative equal to 0. And we discovered that that's equal to 0 at x equals plus or minus 2. So there are our critical points at x equals plus or minus 2. Normally, we would then do a bunch of testing. We would see what was going on. We would draw, our little chart. But in this case, if I take the second derivative, I get 6x. And the second derivative at negative 2 is negative 12. And the second derivative at positive 2 is positive 12. And since this is greater than 0, this implies that there is a minimum here. And since this is, whoops, what did I just say? I just said that completely backwards. Since this is less than 0, it implies that there is a maximum here. Oops. And since this is greater than 0, this implies that there is a minimum here. So if I wanted to sketch the graph of x cubed minus 12x minus 5, I know that at negative 2, there is some kind of local maximum. At positive 2, there is some kind of local minimum. And of course, since I know the end behavior of a cubic, I could just draw something that looks like that. Now, is that exactly accurate? Of course not. I don't, well, I could go back and I could calculate these points, and I know that this is at negative 5 because that's the y-intercept just by inspection of the equation. But at least I've got the basic shape, and I could find more